My name is Kevin Fowler. Normally when I introduce myself, people always ask, is your real name Kevin? And is it short for Kevin? So proactively, Kevin is my real name, and it's not short for Kevin. So we'll get that out of the way so we can focus on SQL Server Database Forensics. There's some familiar faces. Earlier today, this morning, David Litchfield spoke on database forensics, focusing on Oracle. This talk is going to focus on SQL Server Database Forensics. You might find some techniques that are somewhat similar, though, but there's absolutely a new twist, and there's a few other things that we're going to cover today. The way I've laid out the presentation is at the early part, what we're going to do is we're going to go over a forensics primer, and that's going to cover some key concepts that will help us out later in the presentation when we get down to the nitty-gritty and to the hexadecimal, etc. So the first slide, why are databases critical assets? Databases hold critical information. That point is pretty self-explanatory. Industry trends are scaling in versus out, meaning what people are doing are they're taking numerous database servers and they're consolidating them on fewer database boxes. And in most cases, they're doing this to save cost or for ease of manageability. But what this is doing is it's creating these honeypots, or gold pots, I should say, of information that attackers frequently try and target. Data security legislations and regulations out there. California led the way with SB 1386 a few years back, and I believe now there are 34 or 35 other states that actually have regulations in place that force companies to report data security breaches. Due to this, the database security breaches are front page news. People take them extremely seriously. Some of the larger data security breaches that have come to light recently have been TJ Maxx, which there was 45.7 million credit and debit card numbers disclosed, and of course Card System Solutions that had 200,000 credit and debit cards disclosed. Database forensics is a fairly new concept and term. Whether you Google it, whether you do your own independent research, there's not a lot of information out there in the industry. So when most people do investigations, they take a look at a system that an authorized user has gained access to. In most cases, they assume worst case scenario that anyone on the system did have access to the database and did have access to that critical information. So with the concepts we're going to cover today, I'm going to show you some ways and some different techniques that can help justify exactly what happened on the database server. Traditional investigations often exclude databases. That goes without saying. So based on my illustration here, I have an intruder with wreaking havoc on a database server. And what normally happens is there's evidence that's on the database system. A lot of this evidence is in memory. That memory sometimes is paged out to a file system. Some of the evidence as well is written directly to the file system, and that would be in the form of a system event log or a SQL Server error log. So with typical forensic investigations, in a lot of cases you're going to do your dirty word list searches on memory, on the file system, or review the system event logs and the SQL Server error logs. But there's very little focus today on the actual database files, which are highlighted in red. So that means the actual data files and the transaction logs within the actual database server. These files contain a ton of evidence, and we're going to look at that in more detail today. So this solution, database forensics, in terms of definition, it's the application of computer investigation and analysis techniques, and that's put together to gather database evidence suitable for presentation in a court of law. Some of you might see this as being familiar, but it's pretty much the definition of computer forensics with a database twist to it. Some of the benefits you can actually get from conducting database forensic investigations, or you can retrace user DML and DDL operations. By DML operations, that stands for data manipulation language. So any inserts, any updates, or any deletes, you can actually retrace that through database forensics. In addition to DDL operations, which are data definition language, and that involves changes to the actual schema of the database. So that would be if someone creates a new user account, creates a table, someone adds additional privileges to a user. All of these actions will be tracked under DDL operations, and you can retrace both with database forensics. Another benefit is you can identify data pre and post-transaction. So it's one thing to know, hey, some unauthorized user updated all employees' salaries to $100,000 per year. It's another thing to know what the value is before the update. So database forensics will actually tell you what the data was prior and after the actual transaction took place. Something else you can do with database forensics is you can recover previously deleted data rows. So again, knowing a deletion took place is one thing. Knowing what information was deleted is something else, and all this is what we're going to cover later in the presentation. So with databases, they definitely can help prove or disprove a data security breach. So yes, an attacker had access to the database. Did he have access to the objects that contain sensitive information? If he did, what did he actually do within the database? Did he read data? Did he modify data? Did he delete data? All of these are ways you can determine what happened during a database forensic investigation. The best point with the concepts and the techniques that we're going to cover today are they're designed for the real world, meaning you don't need third-party login applications installed and configured. You don't need previously created DML or DDL triggers that are already in place. All the techniques we're going to cover today don't require any dependency on any of these items. So in most cases, when you do forensic investigations, you're going to come across a database server that's ill-equipped for a forensic investigation, and a lot of these techniques will definitely come in beneficial to you. So starting the forensic primer, database files. The data files hold the actual data within the database. By default, when within a SQL Server database, the name of a data file will be the name.mdf. And all of these MDF files contain thousands and thousands of actual data pages. These data pages have page headers, they have data rows, and they have a row offset array. The row offset array just denotes the beginning of the actual data rows. The data rows contain the actual table data that's in the various database objects. And the data rows that are in place within a SQL Server data page can be either a fixed length or a variable length. Fixed length data rows, the structure is extremely straightforward. For variable length data rows, it's a little more convoluted because there's additional overhead to mark when a column stops and where the next one begins. So today we're going to do it the hard way. We're going to focus on the variable length data rows, and we're going to cover that a little bit later in the presentation. In addition to the data files, the log files are denoted with a .ldf extension, and these hold any data required to reverse transactions. So all the DML operations and your DDL operations are logged within a transaction log, and the physical LDF, or the physical transaction log, underneath the hood contains multiple VLFs, which are virtual log files. A subset of the virtual log files are active at any one given point in time. So a VLF will be active. It will record transactions. When that VLF is full, it will move on to another inactive VLF. This process continues until there's no inactive VLFs that are free, and it will start to write to free space. Space is reclaimed within the transaction log by when a database backup is performed. When a database backup is performed, the active VLFs are marked inactive, and the space is reused. In addition to when a database backup is performed, when someone truncates a transaction log, the same procedure will take place. When a transaction log grows to 70% of its capacity, the same operation takes place as well. So SQL Server has these internal routines that help manage the size of the actual log files. And when truncation needs to happen, truncation happens at the VLF point, meaning the VLF is a truncation boundary, If there's a VLF with 100 transactions recorded in there, one transaction is still active, SQL Server will not inactivate that VLF. It will keep the entire VLF active. And according to Microsoft, although you might assume that reading the transaction log directly would be interesting or even useful, it's just too much information. Today, we're actually going to take a look at the transaction log, and we're going to make sense of too much information, according to Microsoft. Based on research I've done, no one has documented the innards, for lack of a technical term, of the transaction log. So I've gone ahead and done that for you today. Inside the transaction log contains over 100 data elements, meaning 100 columns. What that means is each transaction that's recorded within the transaction log can contain 100 different data elements. We have an hour and 15 minutes today, so of course we're not going to cover all 101 data elements. But what we will do, we'll focus on the data elements highlighted in red, which are operation, transaction ID, page ID, slot ID, offset and row, SPID, row log content, 0 and 1. As opposed to giving you guys the definition of all of these transaction log items now, what I'm going to do is throughout the presentation, when we come across the actual element, we'll discuss it then. That'll make it easier for you to comprehend the principles behind that. First one we'll start off with is a SPID, which is a server process ID. What a SPID is, it's used by SQL Server to track a given session within the database. So SQL Server itself uses SPIDs to track what it does internally within the database, and it does the same thing for any user connections that are external to SQL Server. Any transaction log activity is logged directly against the executing SPID, so that helps us definitely for computer forensic investigations. In addition to SPIDs, data type storage and retrieval is something that we should definitely be aware of within SQL Server. SQL Server supports 31 different data types. Various data types are stored and retrieved differently within SQL Server. Little end-in ordering is applicable to selected data types, just like on Microsoft operating systems. SQL Server uses the same end-in ordering. And storing and retrieving the value 21,976 in various data types results in the following. This is an example of how data is stored and retrieved with SQL Server. So using the character data type, the on-disk value is 32, 31, 39, 37, and 36. What this is this is the hex representation of the ASCII equivalent of 21,976, meaning 32 maps to the number 2, 31 maps to the number 1, and so on. So character is pretty straightforward in terms of the way it's stored and the way it's retrieved by SQL Server. Integers, the on-disk value is D855. Of course, because an integer is converted to a decimal, we would need to convert that to little end-in ordering. So D855 in reality is 55D8. That hexadecimal number converted to a decimal brings us to 21,976, and that's what SQL Server does in the background when we retrieve that value. Date time, like integer, is a hexadecimal representation of a decimal number. So D855, again, we'd swap the bits, and that would be 55D8. When you convert that to a decimal, that comes up to 21,976. However, what SQL Server does is it retrieves March 3rd, 1960. The reason it does this is SQL Server, when it deals with date time, it takes into account the number of days since January 1st, 1900. So 21,976 days after January 1st, 1900 brings us up to March 3rd, 1960. A little convoluted, but it works for Microsoft, so be it. And so that's why it's important to understand the differences in the way data types are stored and retrieved by SQL Server, especially when you're looking at the hexadecimal. You need to understand what was stored and what was retrieved. The procedure cache contains ad hoc and parameterized statements. So before SQL Server will execute work, it definitely wants to make sure it has a plan to make sure it can perform the statement in an efficient manner. So if you issue a statement against a SQL Server, selects column 1, 2, and 3 from table A, SQL Server will take a minute and say, what's the best way for me to execute this statement? Are there indexes I can tap into? Should I just do a table scan? So it goes through a lot of compilations and work in the back end, and what it does is it puts together an execution plan. This execution plan is kept in conjunction with the actual text that was executed by the SPID. And this is stored within the procedure cache. And by tapping into this procedure cache, we can actually determine after the fact what statements were executed within the SQL Server. Parameterized statements are just like the ad hoc statements. Something I don't think I clarified was ad hoc statements account for selects, inserts, updates, and deletes. Parameterized statements as well account for inserts, selects, updates, and deletes. However, what SQL Server does with parameterized statements is any literal values SQL Server finds, it will replace with an actual variable. And it replaces that with a variable in order to reuse the plan multiple times in order to save time in execution. Next, database evidence repositories. SQL Server data resides natively within SQL Server and stored externally within Windows. Those of you who have worked with SQL Server know that SQL Server is heavily intertwined with the actual native operating system of Windows. Some of the evidence repositories that you can tap into for database forensic investigations, we're going to focus on the ones in red. However, I'll talk briefly about all of the repositories today. So volatile database data. These are the sessions, the connections, the logged on users, the running processes that are active within SQL Server. All these contain evidence and database information that can help in a forensic investigation. The database data files we discussed, the log files we discussed, the plan cache we tapped into as well. The data cache, SQL Server does not allow direct access to any index pages or data pages. So what SQL Server will do is it will read index and data pages into memory. This area of memory is called a data cache, and any statements that are executed against SQL Server tap into this data cache. Indexes, we just talked about briefly. B-tree indexes are used by NTFS within Windows to help organize files and directories. SQL Server, if it's not broke, it doesn't fix it. SQL Server does the exact same thing for its internal indexes. And the same benefits you get from traditional forensics and tapping into the NTFS B-tree indexes are the same benefits you can get within SQL Server. Excuse me. Next, the version store. SQL Server 2005 introduced a version store. What the version store is depending on the isolation level you have your SQL Server configured to use. SQL Server will record previous versions of data rows. So this, again, is another repository that we can figure out the history of data prior to modifications. Within the operating system, trace files, SQL Server has a default trace file. It runs by default. As soon as you start your SQL Server instance, it records authentication information, DDL operations, etc. System event logs, that goes without saying. It records authentication information, server startup, restarts, etc. The SQL Server error logs as well contain the same information. Is that a question? Nope. Okay. Stretching. I got you. No problem. The page file, again, is memory contents, and that's page from memory to the disk, and of course the actual memory in use within the operating system also contains SQL Server data. Some of the investigation tools we can use when conducting a forensic investigation, I've listed a few here. SQL Server Management Studio Express. What this is this is a free GUI that's released by Microsoft, and this allows you to attach database files, log files, and manage a database server or database files. It's the same interface you would find with the retail SQL Server Management Studio, except it's free and it's a little more lightweight. It's definitely instrumental, as we're going to cover later in the presentation when we're looking at the raw data files. SQL CMD, what that is, it's a command line query tool. Those of you who might have worked with SQL Server in the past, SQL Server 7, 2000, might have used ISQL, OSQL. SQL CMD is the next release that has replaced those tools. And what SQL CMD allows you to do is to issue TSQL statements against a Microsoft SQL Server. SQL CMD will log the statements you send to the SQL Server in addition to the results that it sends you back. You can record those logs in various log files, and you can MD5 sum them as well to make sure that they don't change. So that's an excellent tool, and that's freely available from Microsoft as well. Windows Forensic Tool Chest, I'm sure most of you or a lot of you today have used that in the past. It's a collection of Windows utilities that automate forensics, the acquisition of volatile and non-volatile data within the actual operating system. This tool chest can be customized in conjunction with an OSQL, ISQL, or SQL CMD to also gather volatile and non-volatile SQL Server data. And the next slide, actually, I have a demo of that. DD, DCFL, DD. Again, a lot of you today have probably used these tools before. And these tools allow you to acquire actual disk files off the disk and acquire that, whether it's to a network or to another location, and generate MD5 sums of those files. MD5 sum, again, is used in conjunction with the DD or the DCFL DD utilities. Netcap, CryptCap, depending how you're getting those data files and the files you need to acquire off that disk, you may want to send them over the network and use CryptCap or Netcat, so these can definitely be helpful when getting evidence off the database server. WinHex, we're going to talk about this briefly later in the presentation, but when you need to look at the actual transaction log, WinHex is a great hexadecimal editor that you can see the innards of the transaction log. And native SQL Server views, functions, and statements. There's a large amount of views, functions, and statements that are freely available from Microsoft that we're going to tap into in the next upcoming slides that will gather internal SQL Server information and data that's not readily known today. And it's not really a tool, but I decided to include it here. Lots of sanitized acquisition media because databases are extremely large. I cover a few techniques on how to reduce large data sets, but no matter which way you slice it, you're going to need a decent amount of media to acquire some database or transaction log files. So now that we're done the forensics primer, we can focus on evidence collection, which is how to acquire the actual SQL Server database forensic information. Just like a standard traditional forensic investigation, you want to make sure you determine the scope of evidence collection. If you're investigating a case that the span of events is the last week, you don't want to acquire the last 7 years of data. It's just common sense. The more information you gather, the more information you have to go through, so make sure you keep it tight and you acquire only the information you need to. Just like traditional forensics, database forensics, you're going to need to prioritize your evidence collection. Things will change slightly depending on the scenario you're investigating. A rule of thumb, though, I've listed in order here. Volatile database data, so again, your sessions, your connections, active requests, users, etc. Your transaction logs. Your transaction logs are critical in investigating databases, so that's absolutely something you're going to want to acquire extremely early in the acquisition process. Database files, SQL Server error logs, system event logs, and trace files, again, are also items you're going to want to gather extremely early in the process. Next, collecting volatile database data. So we talked briefly a few slides back on Windows Forensic Tool Chest and how it can be used to automate not only operating system volatile data, but as well how it can gather some of the SQL Server data. And the benefits of WFT is it gives you a GUI front end. It validates the binaries you're using. So if you're using in conjunction with SQL CMD, it validates the signature of SQL CMD in addition to hashing the output files you get. So it's a one-stop shop with very minimal customization. Based on the screen we're looking at here, I'm not sure if you can make it up from your Vantage area, but we just have a command that dumped the users from the SQL Server database. It validated the SQL CMD signature, and it hashed the output files. All the database commands that we've automated can be placed as well in the navigation menu on the left of Windows Forensic Tool Chest. So within the area on the slide, I have a list of databases, the connections and sessions that are active within the SQL Server, all the active logins, and any requests that are executing as well. So you can customize and you can tailor this depending on the investigation and the different types of evidence that you want to view and obtain. So once you finish running WFT to acquire that information, of course you're going to want to execute ad hoc statements against the SQL Server. So SQL CMD, again, highly recommended tool of what you should run. Not sure if you can make out the output, but what we're doing here is just executing SQL CMD, connecting to a database server, and just recording information, and we're specifying what delimiter we want to use for the output file. Collecting the active transaction log. Don't just jump right in and try and acquire the transaction log. It's an extremely critical source of evidence, and we're going to want to make sure that we actually do it right. So there's a few steps we have to perform to make sure that we do acquire the active transaction log and all the correct elements. So the first thing that you should do is figure out transaction logs. Any SQL Server database can have multiple transaction logs. We need to figure out exactly where the transaction logs reside on the system. SB help DB in the name of the database. If you execute that command, it will dump all the data files that are associated with a given database. So within the results here, we can see that the MDF file, which is a data file we discussed earlier, is located in the default directory. The log file with the LDF extension is located in the default directory, but as well there's an additional log file in a non-default directory. So it's a good example that data files can be contained anywhere on the operating system and to understand where they're located prior to acquiring the evidence. Once we know where the physical log files are, again we discussed every LDF has multiple virtual log files. To understand the status of these virtual log files, we can run the command dbcc loginfo. What this does is it just dumps all the virtual log files that exist within the LDF file and what the status of these virtual log files are. Based on the screen capture of the results we have down here, on the file ID 2, which is the first transaction log from our previous slide, there is one active virtual log file with the status of 2. So in this scenario where we had a SQL Server with, we'll say, 10 different transaction logs at 1 gig each, if the records we need to acquire are within the active VLF, we could acquire just that one transaction log as opposed to the other 9 gigs worth of transaction space. So again, just ways on how to reduce the scope of the evidence you acquire. So once we know where the transaction logs are stored, what the VLF status of these transaction logs are, we can actually obtain or extract the records that are loaded within the actual transaction log. FinDBlog is a function that's new within SQL Server 2005, and it's extremely flexible, and you can execute fantastic queries against this. What you can do is, depending on your investigation, if the investigation is around a given object, again, I'll go back to the scenario, someone modified the HR database table, you can look at a transaction log file that's, we'll just say 10 gig, and tell it, just give me all the transactions that modified this HR database table, and it will dump just those transactions for you. Or you can tell it, just dump specific columns. Based on earlier in the presentation, there's over 100 columns. If we're going to focus on 8, we can dump just those 8 columns. And as well, you can focus on just a SPID. If that SPID is tied to a user in question, you can dump all the transactions that user actually executed within the database, or all transactions within a given date or time range. So it's extremely flexible, and it's brand new within SQL Server 2005. DBCC log has been with SQL Server since SQL Server 6.5. It's more resource intensive. It dumps the transaction log in its entirety, so there's not a lot of flexibility in terms of filtering records. What it does come with, though, is some default filters, which you can specify minimal information, slightly more information, full information, detailed information. Based on my experience, option 3 is the best for DBCC log, just based on the level of detail it gives you, the output, and as well, it gives you the hexadecimal dumps as well, so that's pretty, it's pretty handy. Moving along with evidence collection, collecting the database plan cache. The following query, select star from sysdm x cached plans and cross-applying the SQL text plan. What this does is it dumps all of the execution plans within the SQL Server plan cache. And what the second part of that query does is it dumps the actual text that was executed that created that plan. So you can look at a hash bucket or a SQL Server plan execution, and you can look at the actual statement that was executed in plain text in English against the SQL Server. So it's highly recommended to include the SQL text within that statement. In addition to the plan cache, the default statement up above, the additional plan cache specifics, the below two queries, the select star from sysdm execute query stats, and the other one executing against the plan attributes, allow you to dump additional details, including the user who belongs to the schema who executed that query, the date the query was executed, the last time the plan was used. These are all facts that you can extract as well based on plan cache entries by executing those additional two queries. Collecting database data files and log files, by default they're stored in the MSQL data directory under the .mdf or LDF extensions. Self-explanatory how to acquire those. You can use your DD, DCF, LDD, any tool of your choice. Same goes with the default trace files. They're located within the MSQL log directory. And these trace files carry the name log underscore, then it'll be a number, .trc. Every time the SQL Server service is restarted, the number is incremented by 1. So if we have a log underscore 1.trc, we restart that SQL Server service. A new log file, log underscore 2.trc, will be created. So you're going to have a history of all the default trace entries that have occurred within that SQL Server. In addition, SQL Server error logs also within the /log directory. The name of this file is just named error log. When the error log is full or the SQL Server service is restarted, the existing error log is renamed to errorlog.1 and a new error log is created. And it maintains a history of up to 7 error logs. So you're going to want to require all error logs, assuming that's within the scope of your investigation. Collecting system event logs, that's self-explanatory. You can collect the EVT files, or WFT automates that for you if you decide to run that earlier in the investigation. Now that we've gone over how to collect evidence, a primer of evidence, now we're going to go into how to actually analyze it. We're getting to the good stuff now. Windows Event Log, touched on this briefly before, but what it records are authentication data, so failures, successful logins, log-offs, SQL Server startup and shutdown activity, and as well the IP address of SQL Server client connections. With SQL Server, there are many protocols, many ways to connect to a SQL Server. You have TCP/IP, you have shared memory, and you have name pipes. With SQL Server logging, TCP/IP, it will record the actual IP address within the Windows event log. Shared memory, it's interactive, so you have to look at who is logged into the actual database server. But name pipes does not record the IP address of the machine that is connecting to SQL Server. However, if you do run Windows Forensic Tool Chest, it does dump all the connections and sessions within the Windows level, and you can map that back to figure out who was writing that name pipe and connected to that SQL Server. The error log records the exact same information as the Windows event log, the authentication data, startup and shutdown, and the IP address of TCP/IP connections. The advantage of two different log sources are they have different retention periods. Again, error log when you restart it, and Windows event log, it's based on how you customize it by size, by date, etc. But you can compare log file against log file. In some cases, a log file might become corrupt or it might be tampered with. So it's good to have two different sources of the information when conducting an investigation. The default database trace, again, it includes authentication history, but in addition, it actually records DDL operations. So if someone creates a table, that's going to be logged within your default trace. If someone creates a user or grants privileges to that user, that is recorded in the DDL trace as well. And IP addresses of SQL Server client connections, again, is recorded. The application that was used to connect to the SQL Server, to the best of Microsoft's ability, is recorded within this as well. So based on the example we have here under the application name column, we have OSQL32, which is the name of the application that was used to actually connect to SQL Server. One of the most important elements of this default database trace is it maps a SPID, which again is how SQL Server distinguishes who's doing what within the database. It maps that to an actual login name. So that's extremely beneficial to put a name to SPID 51, 52, 53, etc. Data files and log files for evidence analysis. What you should do is just attach the data files, self-explanatory, and these are going to be used to obtain on-demand schema information, data page contents, etc. And the very next slide, throughout the rest of the presentation, we're going to take a deep look into the actual data files that we're attaching. And the active transaction log imported into Excel or Access for viewing. Excel has limitation, I think 65,000 rows, so you might want to use Access or some other database to look at the actual transaction log files. Once they're dumped, you want to identify the DML and DDL statements, in addition to map the transactions to a given SPID. So now we get to the nuts and bolts of what's going on within the transaction log. I'm looking at an update operation. The transaction log contains multiple columns. Operation is exactly what type of transaction was executed within a database server. The begin transaction and commit transaction note the beginning and the end of an actual transaction. In the middle contains exactly what type of transaction it was. So a modified columns equals an update by SQL Server. Transaction ID is an identifier used by SQL Server just to group like transactions together. Page ID, and transaction ID is a hexadecimal representation of the transaction ID. Page ID, what that is it references the actual data page that was modified by that transaction. Again, that's a hexadecimal representation of a decimal page identifier. Slot ID is the actual row within the data page that has been modified. Offset and row is the area within the row that was actually modified. So in most cases, offset and row will tell you exactly what column within a table, within a data page was modified. So putting it all together, looking at this slide, we have one transaction that modified 3 records on 3 different database pages. 3 different rows on 3 different database pages, but the same column was updated within this transaction. So that's at a high level, putting it together, and we're going to take it to the next level on the very next slide. DBCC page will dump the actual contents of a data page that was modified. So based on the previous slide, the page ID of the first transaction was 211. So if we add that as an argument to our DBCC page, what that will do is that will dump the data page, and below the actual page header will give us the object ID. That object ID is the owning object of the data page. Just because we know the data page, we have no idea what object that data page belongs to. Looking at the header will give us the actual object ID. We throw that object ID into a statement, simple select star from sysobjects, and that will tell us the actual object that was modified. So if we look at the results, the order table, X type equals user table, so the order table was modified as part of that transaction. Now that we know what was modified, we need to know exactly what was done to it. And before we do that, we're going to need to figure out exactly what the schema is. So in order to get the schema of the order table, we can dump the following query, select call order, name, data type, etc. from syscolumns, where the object ID equals the object ID that we gathered from the transaction log. What this does is it dumps the order ID of the columns within the actual database. It's extremely important that we understand the order of columns within the database. When you create a table, the order you specify, the different columns within the table, dictate how SQL Server will actually write data to that table. So once in the upcoming slides, we're going to look at a lot of data elements that are written to the table. The order that the data elements are written are denoted here within the call order. If you look at credit card number, which is call order 9, and ship status ID, which is call order 11, 10 is missing. If any modifications are made to the database table, meaning if someone drops a column, it just removes that line from the results. So the order is still correct, but you might come into account, hey, I'm missing a 10, I'm missing a 9. What happened here? It just means someone performed a schema update and removed the column after the table was originally defined. And in addition to the order, we can gather the list of the data types that were in use. Again, SQL Server stores data differently, retrieves data differently, depending on the data type in use, and the length. By looking at the results here, we see some varchar, which are variable length, and we see some integer and date time, which are fixed length. So SQL Server takes the high water mark, and even though it includes fixed and variable length columns, it will store that column as a variable length row. So again, looking at the DBCC page with the 211 argument, which is the data page that was modified, we can actually figure out slot 20, row offset 80, exactly what was done to that data row. So if we look at the starter transaction, that's circled in red here, that's the actual data that was added to that data page. But as well, if we look at the DBCC page output, it's not captured here on this slide, but it also tells us what the start of the actual column was. So the start of the column was actually prior to the data modification. The reason this was done is SQL Server's intelligence, depending how you look at it, it's either intelligent or lazy. If it sees a value on a data page and it's the same value that it has to write in the same position, as opposed to writing the same value over top of the existing value, it will skip writing that value and just increase the offset by 1 and start writing any changes to the actual data files. So jumping to the next slide here, looking at row log content 0, which is what the data was before the modification, and row log context 1, which is what the data was after the modification, what the actual modification did. So if, based on the previous slide, the price column is what was updated. Row log context 0 was 500.00. Row log contents 1 was written decimal 50, and the 20s in hex translate to spaces. And SQL Server put those spaces in just to overwrite the other information that was there so it didn't skew the results. So by looking, adding the last 3 slides together, the first record that was affected by transaction 814 had the price column updated from $3,500 to $3.50. And the reason why that 3 comes into play is, again, the offset on the previous slide had a leading byte of 33. That 33 is the hexadecimal representation of a 3 in ASCII. So when doing log review or log analysis with SQL Server Database Forensics, it's not good enough just to look at the transaction log. You have to take what you get from the transaction log and also compare that to what's on the actual data page to understand the full picture of what the transaction was. If you focus on just a transaction log, in most cases, you will be okay, but you will come up to some situations where you're going to get an incorrect value because you didn't reference what was on the actual data page, and if SQL Server is smart enough not to write a value over top of the existing value. Does that make sense? Yes, sort of. Okay. Next, insert operations. Again, we see the begin transaction, commit transaction. Insert rows. This, of course, is an insert statement. Again, we track the transaction ID. We got the page ID, so the actual page that had the data row inserted into it. And the slot ID, meaning what slot, what row within that data page has been inserted. The offset in row is null, of course, because we're inserting an entire row as opposed to just a column. So in order to figure out exactly what was done in the insert statement, you need to reconstruct the data row. So looking at your transaction log, row log content 0 contains the following string. This string might seem pretty intimidating here, but what this is the actual data row that was inserted as part of that transaction. And to understand what that data row is, we're going to need to know how SQL Server stores information within that data row. So again, looking at the schema as we did earlier, it's the same order table. And to reconstruct the data row, we need to understand, again, what that structure of the variable length data row is. I don't want to go into too much detail here, but the gray bits are overhead. And the areas I want to focus on are the fixed length columns, which are highlighted in yellow. So all of the fixed length columns are stored in the order of the call order results that we got earlier. And any variable length columns are one huge string that's stored at the end of the data record. And item 7 is a row offset, and that marks the end of each variable length column. So for each variable length column, there's going to be a 2-byte value within block 7 that tells us exactly where each variable length column will end. So it will tell us where one column ends and the next column begins. So taking that into consideration, again, I kept the same colors in the slide for you. The overheads in gray. Then we have our fixed columns in yellow. So we have the order ID column, the city column, the state column, the zip column, ship status ID column, order date column, and the price column all together. We have additional overhead. And just before the first blue box, which is first name column, we have the positions where the variable length columns end. So if you take a look, you can see the actual, let's see if I get my mouse going here. So we actually have the 2-byte representation of exactly where the variable length columns end that are highlighted in blue. So the large string of data we had before, we can actually slice and dice based on how SQL Server stores data within a variable length data row and figure out exactly what hex belongs to what column. Now that we have the hex representation, we know the schema of the table. We're going to swap the end in bytes. We're going to translate the data types, whether that's from hexadecimal to ASCII or from hexadecimal to decimal. And once we translate the types, magic, the inserted record was order ID 4122, and we have the first name, last name, address, credit card number, etc. And this guy inserted a record into a table that bought an Xbox 360 for $4. Not bad. Next, delete operations. For delete operations within SQL Server, when a delete statement is executed, what SQL Server does is it marks the records that are part of the delete statement as ghost. What that means is just a single byte which is switched, and by that byte being switched, it means that that record or those records are hidden from any statements or any results that are returned by the SQL Server. So as long as a record is marked as a ghost, it won't show up in any select statements. It won't be included in any insert, update, or delete statements you execute. The data is still stored within the actual data page within SQL Server, which is great. The bad news is there's a ghost record cleanup process, and this runs every couple of minutes, and it blows away all of the ghost records. So ghost records are fairly rare to come by. The only way I've personally been able to see a ghost record is to start a transaction, not commit it, that had a delete operation, and then examine the actual data page. And you can actually see that ghost record there. As soon as you commit the transaction, usually a couple seconds later, that ghost record is gone. But more good news, if we look at the delete operation within the actual transaction log, the delete rows, we get the page ID that the row was deleted from and the slot that contained the original row, but the row log content 0 contains the same structure, which is the actual data row that was deleted as part of that transaction. So following the same process we followed earlier with the update statement, or the insert statement, excuse me, we can use the schema of the object that we just deleted the row from. We can map the hexadecimal to the appropriate columns, the appropriate overhead areas, and we see the same order ID, column ID, city column, etc. We translate the bytes, data types, and we can figure out exactly what that deleted data record was. And this record was for a 62-inch plasma TV for $3,500. So in terms of the transaction log, we just walked through how to retrace inserts, updates, and deletes. And now what about selects? The select statements are stored within the plan cache. The goal for that is just to review applicable statements within the scope of the investigation. So if the scope of the investigation is within the last 24 hours, you want to take a look at entries that were logged, of course, within that period. And any database that's the back end to an application, applications today, in most cases, developers are extremely efficient in how they write queries, meaning they're only going to select the correct columns that they need and provide adequate criteria against that to limit the results that come back. So by examining the plan cache, you're going to find a lot of activity that might be select star from credit card numbers, meaning when an attacker gets access to a database that he's not familiar with, he's going to need to do some sort of reconnaissance to figure out what the structure is, what type of data is stored within that database. There's going to be a lot of select star from this table, select star from that table, and that's going to light up the plan cache for you. And by dumping the plan cache, you can track these actual statements that were executed. Again, the inserts, the updates, the deletes, and map that to a SPID, and from there to an actual database user. Investigation pitfalls. What to look out for. Know the schema you're working with. When you're looking at the raw hexadecimal, things get real ugly real quick if you don't understand the schema behind the object that you're trying to translate. Once you know the schema for the object, you of course need to know what data types are involved, how values are stored, and how they're retrieved by SQL Server. Reduce large data sets. No one likes looking at hexadecimal, so the less time you have in there, the better. And again, correlate on-disk values with transaction log data. Don't just look at transaction log data, because you can get burned and provide results that are inaccurate based on information that was on the on-disk value. Encryption. SQL Server 2005 introduced encryption, which is native. There's various ways you can encrypt data. Symmetric key encryption is the most popular. When you're looking at hexadecimal and you try to translate, you understand the schema, you understand the data types, you try and translate what's going on, and you're not making heads or tails out of it, there's a good chance that data might be encrypted, because SQL Server encrypts data prior to writing it to the log, prior to storing it within a database table. I'm actually contributing author of a book which is titled How to Cheat at Securing SQL Server 2005. I wrote the chapter on data encryption. Within this chapter, it shows you how to take a look at ciphertext, which is the actual hexadecimal, how to determine if that value is encrypted. If it is encrypted, what symmetric key was used to encrypt that actual data. Because what SQL Server does is when it encrypts data, it appends the key GUID that was used to encrypt to the actual ciphertext. So there's a script in there that I've written that will actually take a look at a string and tell you if it is encrypted and what key was used to encrypt it. So that could save you countless hours as opposed to racking your head thinking, why can't I translate this simple value? There's a good chance it might be encrypted. And last but not least, it takes time, so be patient. The first couple times, translating a insert statement or a delete statement, going through the variable length data rows might take a while. The more you do it, the better you'll get at it. My first time, I think I struggled for an hour on the first one. Now I can do them in about 10 or 15 minutes, so keep at it. Absolutely, absolutely. You can automate it. I wouldn't recommend automating it until you understand what's actually being done in the back end. Because when automation doesn't work or anti-forensics, you have to understand how it's done in the back end, exactly what's happening at a low level. But absolutely, it can be automated extremely easily, actually, in script. So, conclusion. Don't ignore the database when conducting forensic investigations. As we covered before, in the past, a lot of forensic investigations focus on just the event logs or the SQL Server error logs, but not the actual data files. There's a ton of information within data files and log files that just need to be gathered. So gather it, analyze them, get the information you need. That will help support the case that you're working on. On all of your DVDs that you got with Black Hat, I have a white paper in there, and that covers a real, well, it's a simulation of a real-world database forensic scenario. So it goes over when you get the initial call, when you're on site, how to validate something happened, how to acquire data, how to analyze data, how to set together your timeline of events, and the actual report. So it takes you through the process from end to end, which is extremely helpful. In addition, again, we had an hour today. I couldn't cover everything in the presentation, but there's additional collection and analysis techniques as well that are all over the white paper, including code pages and correlation settings. SQL Server has multilingual support. You could have several tables from several different languages to understand what language you're looking at and how to translate that. I cover that within the actual white paper. In addition, one of the languages, if you store information in Japanese and you view that Japanese information on your forensic workstation that's configured in an American code page, you're going to get incorrect information. You're going to get corrupt data. So how to make sure you understand what the correlation setting of the target table is and what code page you're using on your analyst workstation is covered in the white paper. How to obtain server configuration. Identify user account creation and elevation of privilege activity, as well as covered within the white paper, and transaction log data carving. We talked in the presentation about how to take a look at the active VLF and how to extract data. That's what we did when we dumped the log file. But when active VLFs are inactive, how do you get access to those transactions? And that's touched briefly within the actual white paper and more. Questions? Up at the front. Well, with the trace files, the database files, meaning the MDF files and the log files, all of them are held by SQL Server. So you would actually have to stop the SQL Server processes to grab those files. That's why, based on the evidence prioritization, you gather all the database evidence information first, stop the services, and then do your signatures, grab the files, and take it from there. Past trace files, though, of course, there's no lock on them. And you can, of course, gather those. Okay. I'm getting off easy here. Any more questions at the back? Yeah. I got you. That's actually a good question. In case anyone didn't hear it, what's the lifetime of the procedure cache? How long does it store information? To answer that, SQL Server will store all the plan execution and all the text that was executed as long as the last reboot. In most cases, it stores it all. However, if it does come into a situation where there's memory pressure, meaning it runs out of memory, it will start to overwrite the procedure cache. Assuming your memory allocation is fine for the specs of your SQL Server, it should carry all entries as of the last restart of your SQL Server. Okay? Correct. With log files, the correct response to that would be it varies. If you back up your log file, it marks all active VLFs as inactive. If your log file fills up to 70% of the actual size of your transaction log, it will complete the same process. If you back up once a week, then your log files will contain 1 week of data. So it varies depending on numerous conditions, in addition to if the number of transactions that have been recorded, if it takes longer than your set recovery interval to restore those transactions, of course it will mark active ALFs as inactive. So there's about 4 or 5 different variables, and the only answer I can give you is it varies. It could be hours, weeks, days, depending on a whole bunch of different factors. That's why it's important to get in there, and that's the second item you should grab after volatile information, is grab those transactions, because they're so important with an investigation. Okay. Anyone else?
So no tools out there as far as you know to assist with debugging of the files?
0. I actually started writing one, but I had to stop. This tool was actually going to automate the acquisition of database files, evidence, and as well, I was going to search for rootkits, a few other things, and in addition to that, help analyze, but I actually ran out of time and I haven't written the tool yet. But I had the question earlier, automation can be extremely easy for this because it's repetitive, depending on the different variables within the situation. So no tools today, but I'm expecting a lot in the future because it's extremely easy to automate.
And on that one slide, you mentioned the Windows Forensics Toolkit. I missed what you were saying the use of that would be in this scenario.
Oh, for a forensic toolkit, or tool chest, what it is a suite of tools that you basically have a configuration file, and you run on a Windows server, and you would just hit go, and it would go through memory, disk files, etc., and it gathers volatile and non-volatile data. You can customize Windows Forensic Tool Chest with any executables you want. So by adding SQL CMD or another command line SQL query tool, you can tell it what type of evidence to extract. Windows Forensic Tool Chest will extract that information, store the results, and MD5 sum them as well to make sure you have integrity of those files. So that's what I've done in the investigations that I've actually conducted, and it works extremely well. And a lot of times during the investigation, you're going to come up to the fact, oh, I wonder what that registry setting of that database server was. All that information is within WFT. So you'd be silly not to automate collection with WFT, even for database forensics. Cool.
And since you have to, I guess, stop the server to get some of this data, I guess if there are any issues there in terms of proving apart that you didn't, modify the data as you were acquiring it.
If I understand the question, it was when you stop the server, is there any way to make sure you don't modify the data?
Yeah, ideally, when you're doing the acquisition, you show that you've shut down the server and you're kind of taking the data off.
Yep.
In a read-only fashion.
Mm-hmm.
It's relatively provable that you didn't introduce data that wasn't really there as you're doing your acquisition. It seems like you can't do that quite as much with the database.
For the information you gather before you obtain the physical MDF data files and log files, it's live analysis, so you're just dumping live information, so that's fine. To grab the existing trace file, the existing error log file, and the MDF and LDF files, you will have to stop that. But I don't see how that would introduce a lot of changes for the file. And as long as you record what time you shut it down, it's not going to add entries that this transaction deleted a certain record or inserted a certain record. When you do grab those data files, though, this is actually bringing up a good point. When you acquire that file, if you're using DCFLDD, you want to make sure to use the block size and set an appropriate block size, because when you attach that to your actual SQL Server Management Studio Express, it will modify the page header. So as long as you use a block size, you can discount the area that's been modified and make sure you still have integrity for all of the data pages that you actually analyze. So it's a good question. Anyone else? Great. Thank you very much. Enjoy the rest of the conference.